Previous installations.
It's okay, that's Russian. Привет. How are you? Oh, well, hundreds of things. New? Yes. No, it's not. It's like, hey, wow, maybe 1 year and a half. So it's like, yeah, it's like mine total. Absolutely showed me. Oh, I love short highlights. I really love Сергей, я не уверена, что напишет. Я не уверена, что напишет. Что? Я не слышу.
So thank you everybody for coming. Today we have defense of PhD dissertation of my student Evgeniya Predybaylo. So the committee consists of myself, Professor Bart, and Professor Schuster. So our external examiner is in New Jersey, I guess. Where are you, Alan?
Yeah, I'm in New Jersey.
Yes. So, fortunately, we can make it in remotely. Alan is teaching, cannot come in person, although he has been here a few times. Okay. So the defense will be in this format. Jenny will give a talk for 30-35 minutes, and after that everybody will have time to torture her and ask the most difficult questions. So after that, door will be closed, and and committee will ask questions. The committee chair will be Professor Jerry Schuster. So we discuss new rules at the program. And we want to put to prevent the academic advisor, the research advisor, to be chair. Although I didn't put it in the rules. So Martin thinks it is in the rules, but it is not there. I think we have to vote on this. But nevertheless, so I decided, he asked me and decided that's all well. So let I will follow this. So Jenny is here for several years. He graduated from Moscow Physical Technical Institute. She actually has 2 master's degrees from FISTECH and from KAUST. So after that she began to work on global climate modeling. She used one of the best existing models, couple of models. It was the best at the time of IR4, IPC IR4 report. So now we have more sophisticated GFDL model that works a little bit worse than CM 2.1 in many cases. So it means that sophistication not necessarily the improvement. It makes things more difficult. So sometimes you don't need that many data. Okay. So Jenny's research about effect volcanoes on ENSA, extremely complex dynamical problem. There is multiple opinions how it works, and what she tried to do to put some order and give some definite answers what is working and what is not. So that's roughly. I give the all guidances to how to say all authority to the chair. So you will have option to ask your questions when she finishes. She will finish. Please don't interrupt her on the way.
Okay, so I guess I have to say a few words. She will begin in 1 second or so, but she'll take 35 minutes, and then she'll entertain questions from the audience. And then after about 20 minutes of questions, the audience will leave and the committee will stay behind.
Thank you very much, Gerald, for your kind introduction. And it is really a very important day for me, and I'm really happy that you all joined me here today and support me. So, during my PhD, I was working on the interaction between the two of the main climate drivers on the Earth, the volcanic eruptions and the El Niño Southern Oscillation. The El Niño Southern Oscillation, or ENSO, describes the changes of the temperature, precipitation, and wind patterns in the biggest ocean on the Earth, the Pacific. And it has three major phases: neutral, El Niño, and La Niña. El Niño and La Niña. This oscillation has a period of 2 to 7 years, and El Niño is characterized by the anomalously warm sea surface temperature in the eastern and central Pacific. La Niña is the opposite phase of the El Niño, and it has anomalously cold sea surface temperature in the same part of the Pacific Ocean. El Niño is usually at its maximum in November, December, and each El Niño event is different, but it can roughly be classified into two types: the Central Pacific El Niño or Eastern Pacific El Niño, depending on the location of the warming peak. ENSO is usually described using the Niño 3.4 index, which is the sea surface temperature anomaly averaged over this Niño 3.4 region in the tropical Pacific. Alan, can you hear me? Alan?
Yes, I have my mic turned up. Yes, go ahead.
Okay, good. This is how the historical Niño 3.4 index looked like. And when it is positive, marked in red, it means it was an El Niño year, and when it is negative, it was a La Niña year. So why it is important to study this phenomenon? Because ENSO controls the climate not only in the Pacific Ocean, but also in many other parts of the globe. It can cause droughts, floods, hurricanes, heat waves, and all other kinds of severe events. And therefore, proper projections and predictions of the future ENSO behavior is extremely important to evaluate the future risks. But ENSO is very sensitive to the external perturbations, such as, for example, the increase of the carbon dioxide in the atmosphere or the volcanic eruptions. And the stratospheric volcanic eruptions are the ones that can significantly impact the climate. These eruptions can bring the erupted material up into the stratosphere, where one of the main plume components, sulfur dioxide, converts into sulfate aerosols, which stay in the stratosphere for more than a year. These newly formed aerosols reflect significant amount of incoming solar radiation and therefore cool down the surface around the globe. But they can also absorb thermal radiation and significantly warm the stratosphere. And this what has a severe climate impact. Also, such eruptions can serve as a natural experiment which could help us to uncover the hidden features of ENSO and to understand its mechanism better. The latest eruption of this kind was an eruption of Mount Pinatubo, which happened in Philippines in June of 1991. This eruption injected about 20 million tons of sulfur dioxide into the stratosphere and caused a 2-degree warming in the stratosphere and cooled down the surface by more than half a degree. But it was also observed that the Pinatubo eruption and also El Chichon eruption, which happened a bit earlier in 1982, coincided with an El Niño phase, which is the warming of the tropical Pacific. Was it just a coincidence, or is there a deterministic mechanism behind it? Well, taking into account the limited number of observations, it is difficult to say. However, the paleo data also reported that the El Niño probability doubles after the strong volcanic eruptions. There were already many modeling studies on the ENSO response to the volcanic eruptions. However, there is no consensus yet. And ENSO response can be affected by many factors, such as, for example, ocean preconditioning, the state of ENSO before the eruption, or seasonal timing and magnitude of the volcanic eruption, as well as the location of the volcano. So in my dissertation, I aim to analyze the ENSO responses to volcanic eruptions, taking into account all of them. And with this in hand, I will describe the mechanisms of the volcano and ENSO interaction. For this purpose, I use the climate model CM2.1, developed by the Geophysical Fluid Dynamics Laboratory at Princeton. It is a general circulation model which has coupled oceanic and atmospheric components. The atmospheric part has a resolution of 2 by 2.5 degrees and has 24 vertical levels, and the oceanic component has a horizontal resolution of 1 by 1 degree with refinement to the equator to 0.3 degrees and has 50 vertical levels. This model, as Gary already mentioned, was used for the assessment report 4 of the Intergovernmental Panel for Climate Change, the IPCC, and also for the coupled model intercomparison project, CMIP3. This model satisfies all our experimental needs. It can handle the volcanic eruptions using the prescribed aerosol optical properties. And in this work, I used the volcanic dataset developed by Gera. And it also can simulate the realistic amplitudes and frequencies of ENSO. And this table compares the ENSO phase frequencies calculated from the observations and from the model. And you can see that for each of the chosen ENSO types, the values are pretty close. CM2.1 reproduces a realistic climatic responses to Pinatubo in both stratosphere and troposphere. Here I show the plot of the observed and modeled temperature anomaly after the Pinatubo eruption. The blue line here represents the temperature anomaly from the observations, and the black line is from simulations. And you can see that these two lines correspond very well to each other for both stratosphere and troposphere. With this model in hand, we first studied the ENSO responses to the equatorial eruptions. And this Hope-Mollet diagram, where x-axis is time and y-axis is latitude, shows the distribution of the aerosol plume after the eruption of Pinatubo in 1991. These aerosols originated near the equator and then were distributed towards both poles, covering the whole globe. This Pinatubo eruption is the most observed eruption so far, and it is used as a case study for many climate studies. But before the eruption, ENSO can be in any of its phases, in different phases, and depending on that, its response to volcanic eruption may vary. So I start my research by investigating the role of the ENSO preconditioning, or the state of ENSO before the eruption, in the response to a Pinatubo-sized eruption. For this purpose, we designed the following experimental setup. First of all, to isolate the effect of the volcano, we run two sets of experiments: the control without the volcano and the perturbed with volcano. These two experiments always start from the 1st of January, from the same initial conditions, which lead to one of the desired ENSO phases in December. In our case, it is neutral, Central Pacific El Niño, Eastern Pacific El Niño, and La Niña. Before the eruptions, these two experiments are identical, and they only diverge after the eruption. So each experiment is run for 3 years, and I calculate the ENSO response to volcanic eruption by simply subtracting the control experiment from the perturbed. But we also need to deal with strong ENSO variability, and therefore, to produce a reliable response, we need to run initial condition ensemble simulations. In other words, instead of running a single simulation for an experiment, we run 10 of them and then estimate the distribution of the responses. So I choose the initial conditions from the long control run, which doesn't have volcanic aerosols, as follows. First, I pick 10 initial conditions of the 1st of January, such that they all lead to a neutral ENSO phase in December of the same year. And then I repeat the same procedure for the other 3 experiments, for Central Pacific El Nino, Eastern Pacific El Nino, and La Nina. And these are the results that I have obtained. Here I plot the Nina 3.4 index for each of the experiments, and the dashed green line here represents the control. The blue line here is the perturbed experiment, and red is the difference between them. So these little volcanoes represent when the volcano erupted. So the Pacific has the strongest response to a volcanic eruption during the neutral ENSO phase or the Central Pacific El Nino reconditioning. In this case, we are most likely to observe an El Nino-like response or a multi-year El Nino-like response following the eruption. However, if the eruption happens during the development of the Eastern Pacific El Nino, then we will most probably observe a weak decrease of the potential El Nino amplitude and then a slight extension of this El Nino. La Nina didn't show any response. And as you see, the main finding of this work was that the different El Nino types respond to the volcanic eruptions differently. And therefore, in any analysis, they have to be considered separately. And what is the reason for such a different behavior of the ENSO response? So I'm going to explain the mechanism in the next few slides. This whole-body diagram on the left represents the change of the equatorial surface temperature and wind response to a volcanic eruption, where x-axis represents the longitude and y-axis is time, starting from the time of the eruption onwards. During the, the color here represents the temperature, and the contour lines are the zonal wind response. This cartoon on the right represents the vertical profile of the equatorial Pacific, where on the right there is an American coast and on the left it's Indonesia. So during the neutral or Central Pacific El Nino preconditioning, there is a trade winds blowing from east to west, and there is an upwelling in the east. And when the volcano erupts and there is strong volcanic radiative cooling, the ocean dynamical thermostat comes into play, such that the eastern or western Pacific cools stronger than the eastern Pacific, and this causes a strong temperature gradient over the ocean, which changes the trade winds significantly. It causes a trade wind decrease, which serves as a precursor to the El Nino-like development. However, in contrast with the Central Pacific El Nino, the response of a strong Eastern Pacific El Nino is different. And during the Eastern Pacific El Nino, the warming peak is located in the east, and the upwelling is suppressed. So there is nothing to regulate the temperature in the east, and therefore, when the strong volcanic eruption takes place, the surface in the equatorial Pacific cools uniformly along the equator. And this produces no wind anomaly, and therefore we observe no El Nino-like response. With the same ocean dynamical thermostat mechanism, we can also explain the absence of the response in the La Nina case. And during the La Nina phase, the winds and upwelling are intensified, and the cold water is distributed all along the equator. Therefore, when the volcano erupts, the surface cools slightly along the whole equator, and as a result, again, no wind anomaly and no warming response here. So, despite this mechanism is able to explain all the differences, there were other mechanisms proposed. For example, some studies report that the driving wind anomalies that can appear due to a very strong cooling of the African continent or the maritime and Australia continent. To verify this hypothesis, we conducted additional experiments in which we override land surface temperature over the corresponding continent with the control data and see if the lack of the land-ocean temperature gradient would still produce the El Niño-like response. And these are the Hochmuller diagrams of the all three experiments. So the first column represents the temperature and wind responses after the eruption for the no override experiment. The second column represents the responses in Africa override case, and the third column is maritime and Australia override experiment. The rows represent the experiments with La Niña preconditioning, neutral, weak El Niño, and extreme El Niño. So as you can see, the resulting response patterns are very similar in all cases. And from this we can claim that at least in the CM 2.1 model, the contribution of the land-ocean temperature gradient is very small compared to the ocean dynamical thermostat mechanism, which I explained before. But so far, we have only considered the effect of the summer eruptions. However, the eruptions can happen at any time, in winter, spring, summer, or autumn. And many other studies average the impact of all available eruptions, with no regard to seasonal timing. However, this approach is not quite accurate, and I will explain you why. The main issue comes with the answer predictability itself. So this is an El Niño, which is supposed to develop without an eruption. This is just an example. And at the beginning of the year, it is almost impossible to predict the upcoming El Niño phase. However, after the eruption, the predictability becomes significantly better. So this phenomenon is called the spring predictability barrier. And to account for the spring predictability barrier, and to check the differences between the winter and summer eruptions, we designed this set of experiments with the perturbed forcings. So we took one initial condition, which would lead to a strong Eastern Pacific El Niño in the absence of the volcano, and then we perturbed this initial condition with 50 slightly different atmospheric forcings. We do this in February using very tiny, so-called, we call them butterfly forcings. And then we also perturb them with Pinatubo-sized forcings, which are constructed as Pinatubo plus this little butterfly. And then we repeat the same for June. And in this figure, I show you the resulting Niño 3.4 index. The black dashed line represents the control El Niño that developed without a volcanic eruption. Then gray spaghetti lines show the perturbed answer trajectories, which appeared after we applied the February and June butterfly perturbations. And you can easily see that the spread of the answer trajectories after a February small perturbation is much larger than in the case of the June perturbations. However, let's see what happens if instead of a small perturbation we put a volcano. And as shown here, the spread of the answer trajectories is still the same for the winter eruption. However, it is much smaller for the summer eruption. So therefore, the answer response to winter eruptions is very unlikely to predict, and the response to a summer eruption should be more robust. So this result pushed us to the idea that the ENSO response to strong volcanic eruption consists of the two components, the stochastic and deterministic. And we define the stochastic component as a response to the very small perturbation. And when this component is small, then the ENSO phase is easy to predict. And when it is large, then it is difficult to predict. So in case of the small stochastic component, we will be able to estimate the deterministic component which would appear in case of a strong perturbation. And the deterministic component we calculate as the difference between the total response and the stochastic response. And the stronger the perturbation, the stronger should be this deterministic component. So we decided to analyze the rest of the ENSO responses of the different ENSO preconditionings to different equatorial volcanic eruptions, all in terms of stochastic and deterministic components. And to deal with this strong ENSO variability and strong sensitivity to the small perturbation, we applied a grand ensemble technique. So now, instead of running just ensembles, I run the ensembles of ensembles. And for each ENSO type and perturbation, I use 10 different initial conditions, and I choose them as I showed you before. And then to each of them, I apply 10 different forcings, and this gives me 100 members in each grand ensemble. And we produce these kind of grand ensembles for the following setups. For each of the 6 ENSO phases, ranged by the amplitude, we first study the stochastic component by applying the butterfly perturbations in 3 different seasons, in winter, spring, and summer. And then to study the volcanic impact, we perturb the same initial conditions with the Pinatubo size eruption and the Tambora size eruption. And this Tambora eruption happened in 1815, and it was 3 times larger than the eruption of Pinatubo. It injected about 60 million tons of sulfur dioxide into the stratosphere. This was the eruption that produced a year without a summer. So this big was its climatic impact. So this setup resulted in 5,400 of perturbed simulations, making it the biggest study of this kind conducted. So during the analysis, we actually dealt with 16,000 years of climate data. And this diagram summarizes the responses to all these perturbations. So the first column shows the Niño 3.4 index averaged over the first year after the eruption over October, November, December. And then the second row is the average temperature response over the October, November, December, but the second year after the eruption. And the green dot here represents the control ensemble median. Then this box and whiskers show the spread of the butterfly ensemble with the median here in the middle. And then the red dot is the response to the Tambora size eruption, and blue is the Pinatubo size eruption. So using this diagram, we can estimate the stochastic response by subtracting the butterfly median from the control experiment, and the deterministic response can be calculated as this red dot or blue dot for Tambora and Pinatubo correspondingly, minus this stochastic median. A bit tricky, needs some time to adapt to this figure, but I will just quickly show you the results. So the spread of the February butterfly ensembles is large for all ENSO preconditionings perturbed with the February perturbation, compared to the June perturbation, when the stochastic response will be much smaller. Then the ENSO response to winter and spring perturbations is difficult to detect even for Tambora scale eruption, again because the stochastic component is very big. However, there is one outlier, which is the neutral preconditioning. then the butterfly perturbations may significantly change the trajectories of moderate, strong, and extreme El Niños by making them much smaller than they would potentially be. And then, as I said, the stochastic component of the response is small for the June perturbations, so we can try to estimate the deterministic response of the volcano, to the volcano. And there is a strong, robust cooling after the Tambora-sized eruption in the first year. You can see these red dots are much lower than this green. And this cooling response is usually followed by this strong El Niño-like response observed for the weak and moderate El Niño preconditionings, as I show here. At the same time, the response of La Niña, strong El Niño, and extreme El Niño is much smaller compared to the weak and moderate El Niños. And with these results, I would like to summarize the study of the answer responses to the equatorial eruptions. And now let's move to the final part of my dissertation, where I would like to tell you about the stochastic and deterministic components of the answer response to high latitude eruptions. And in comparison to the equatorial eruptions, the plume of the high latitude eruption is trapped by only one of the hemispheres. And I consider the eruption of Katmai, which happened in Alaska in June 1912. This eruption injected 5 million tons of sulfur dioxide into the stratosphere, and it caused a 1 degree cooling of the northern hemisphere. Also, I will consider the impact of the hypothetical volcanic eruption, which is 3 times bigger than the eruption of Katmai. So we looked at the response of the 4 different ensotypes to Katmai and 3 Katmai eruptions which happened in February and in June. And to estimate the stochastic component, we applied the high latitude butterfly perturbations also in February and in June. And here are the responses that I have obtained. So the stochastic component, in case of the high latitude perturbations, appears to be the same as with the high latitude perturbations, despite differently distributed aerosol plume. And therefore, the effect of the wind eruptions will be also difficult to predict, and therefore I only consider here the effect, the deterministic response to the June volcanic eruptions. So this is the special distribution of the surface temperature deterministic response averaged over October, November, December of the first year following the eruption. And the answer response to the Katmai size eruption is very weak, so it's almost no significant everywhere. But the answer response to the 3 Katmai eruptions is significant. So the deterministic response scales with the increase of the volcanic forcing. In contrast with the response to the equatorial eruptions, in which we first should have observed a cooling of the tropical Pacific, here we detect an El Niño-like response in 4 to 6 months after the eruption. And in case of the equatorial eruptions, this El Niño-like response was much stronger, and it appeared in a year after the eruption. Also, in contrast to the equatorial eruptions, the Eastern Pacific El Niño response here is the strongest, where for the equatorial eruptions it was the smallest. So what is the mechanism for such a response? And the main difference between the response to the equatorial and high latitude eruptions is that the ocean dynamical thermostat that I explained before is not at play here, because we almost do not have the radiative cooling over the equatorial part of the Pacific. However, the previous studies report that the southward shift of the intertropical convergence zone would cause the trade wind decrease, which would lead to an El Niño-like response. However, in my work, we found that this southward shift of the ITCZ is non-uniform, and it strongly depends on the ocean preconditioning, and it also depends on the initial position of the ITCZ. So with this, I would like to summarize the results and contributions of my dissertation. I have discussed the interaction between the volcanic eruptions and El Niño, which are the two of the main climate drivers on the Earth. I have designed the unique experimental framework which allows to separate the stochastic and deterministic components of the answer response, and the partial contribution of these two components strongly depends on the timing of the eruption. Answer response to all stratospheric eruptions strongly depends on the answer preconditioning, with no regard to the location of the volcano. However, the mechanism of answer response strongly depends on the location of the eruption. And in case of the equatorial eruptions, we found it to be the ocean dynamical thermostat, and in the case of the high latitude eruptions, it is the zonally non-uniform shift of the intertropical convergence zone. And the results of my dissertation help explaining the inconsistencies between the previous modeling and observational studies by pointing out the inaccurate time compositing and the ensemble design. So the first part of my work, where I looked at the answer response to Pinatubo size eruption, is already published in Journal of Geophysical Research Atmospheres. And in summer, I have submitted the second paper on the grand ensemble test of answer response to equatorial volcanic eruptions, and it's now in review in Science Advances. And the third paper, which is the answer response to high latitude eruptions, is still in preparation. However, I plan to submit it before I leave in December. And I have reported these results on several international conferences, and I also gave the seminars at Max Planck Institute for Chemistry, Rutgers University, and Geophysical Fluid Dynamics Laboratory at Princeton. And here is the to-do list for my future work. I plan to continue my academic career at Max Planck Institute for Chemistry, where I would like to learn the new techniques and gain valuable skills from the expert in atmospheric chemistry. And I would like to use these skills to do the realistic interactive simulations of the volcanic plume in the MPIC model, which is called EMAC. And I would like to apply this to study the role of the effect of the volcanic eruptions and their interaction with ENSO in the future. And with this figure, I usually finish all my presentations, but today I would like to finish it with this figure. And first of all, I would like to thank my professor Gera for his patience and knowledge he gave me, and also that he was not as an advisor for me, but more like a father who was always there for me for ups and downs. He would listen to all my concerns, personal and scientific. And I would also like to thank my best collaborator in the world, Andrew Wittenberg, who would always come up with interesting ideas and give me valuable feedback, and also improve my English a little bit when writing. Also HPC team, which helped to solve all the supercomputing problems that always pop up, during work on the supercomputer. And also my husband, who walked all this way hand in hand with me, and he was listening to my cries and laughs during the work. And my mom, who loved me and supported me for all my life, and without her I would not be standing here defending my PhD. And all these people made my life at KAUST better. Thank you very much for coming and listening to me today.
So we'll take questions in the audience for about 30 minutes.
Yes.
I have just a curiosity comment and a question. So we'll start with the curiosity comment. The reason why it is called El Niño, it's because in South America, and appears also in December,
Yes.
it's because in South America we don't have Santa Claus or St. Nicholas, but the baby boy, the baby Jesus. And because it appears in December, they just related with the arrival of the baby boy in Christmas, and La Niña was the baby
Is the girl.
Yeah.
Yeah.
And my question is more like, so you had there in the future work, well, previous slide.
Oh yeah.
The future work,
Oops.
the role of these eruptions and these interactions with climate change. So I guess we need a very big eruption to
Yeah, we need
reduce its
about
impact.
the size of an eruption of Pinatubo at least.
Okay.
Because Pinatubo is like the smallest size that can impact
Affect it, yeah.
and so on.
And so you're showing just, it has just a very short-term, 1-year term effect, or do it have more?
It has a longer effect. It depends on what we consider atmosphere or the ocean. The effect on the atmosphere is for about 2 years, and then effect on the ocean is longer because ocean has a longer memory. When it is impacted by something, in this case it's radiative cooling, it will keep this cooling for
Yeah, Lucille.
about
Heat,
10
yeah.
or 20 years.
Thank you. Wonderful presentation.
First of all, congratulations on the outstanding talk. The experiments were very well designed. However, I beg to differ with you about the hypothesis for the effects you saw. In particular, I think you dismissed the monsoon effects rather cavalierly, in my opinion. By prescribing surface temperature to the control value is not the way to get rid of the monsoon, because the surface temperature gradient is important only in the pre-monsoon phase, when dTdy is important and the temperature land surface is very hot at that time. Once the monsoon is set in, dTdy becomes ineffective because of the rain, the soil moisture is